Traditional trace-based garbage collection relies on a brutal premise. To safely identify and clear dead memory, the entire system must halt. The technical logic behind this requirement is straightforward. An accurate reachability analysis demands a static, unchanging object graph. If the graph shifts while the trace is running, the results are mathematically invalid. The source of that shifting is the active user program, known as the Mutator. The Mutator is continuously allocating new memory and altering the references connecting existing objects. Forgiving applications can tolerate a brief pause while the collector traces the static graph. But as heap sizes scale into the gigabytes, these monolithic tracing cycles cause unpredictable, unbounded execution pauses. That latency destroys the viability of real-time applications or high-frequency trading platforms. Achieving massive scale with strict latency limits requires abandoning the mathematical safety of the stop-the-world trace. To eliminate the monolithic pause, system architects divide the tracing workload into discrete, manageable units. That exact division happens along two axes, time and space. This timeline illustrates temporal division, or incremental collection. The garbage collector interleaves tiny execution blocks directly alongside the Mutator thread. Below the timeline is spatial division, or partial collection. The collector restricts its analysis to highly profitable subsets of memory, ignoring the rest. Both of these strategies keep the application responsive. Both also deliberately violate the stop-the-world assumption, meaning the Mutator is now actively modifying the graph while the collector is trying to analyze it. Modern short-pause garbage collection is an exercise in engineering around this chaos. System architects trade raw CPU cycles and memory overhead to safely manage concurrent graph modification. To understand the cost of that trade-off, we have to look closely at the mechanics of an incremental trace, where the collector and the Mutator operate simultaneously. This directed object graph maps the three states of an active trace. The collector starts at the roots, moving objects from the unreached pool into the unscanned pool, and finally into the scanned pool once all their outgoing pointers are analyzed. The vulnerability arises because the Mutator is running in parallel. It can intercept the graph ahead of the trace and sever a pointer that connects an unscanned node to an unreached node. The Mutator then takes that severed pointer and writes it into an object that the collector has already finished scanning. By definition, the collector does not revisit scanned objects. The trace progresses, completely bypassing the unreached object hidden behind the scanned node. Because the Mutator rewrote the graph behind the collector's back, a naive incremental approach will inevitably classify active, reachable memory as dead, causing catastrophic memory corruption. The standard engineering fix for this hazard is a compiler-injected safeguard called a write barrier. Looking at the same graph, the write barrier constantly monitors the Mutator's actions. When the Mutator attempts to write a mu reference into a scanned object, the barrier intercepts the operation. Upon interception, the barrier forcefully reverts the scanned object, dropping it back into the unscanned pool. This guarantees the collector will path through it again. This fallback mechanism keeps the memory safe, but it makes the algorithm structurally conservative. To ensure it never deletes a live object, the incremental collector routinely overestimates the total set of reachable data. That overestimation generates what architects call floating garbage, memory that genuinely died during the current trace, but is intentionally preserved until the next cycle to guarantee algorithmic safety. Low-latency systems explicitly prioritize this safety over precision. They accept the overhead of executing write barriers and retaining floating garbage to prevent the system from freezing. Spatial division operates on a different compromise, rooted in the generational hypothesis. Most newly allocated objects die within a few million instructions. Generational garbage collection leverages this by partitioning heap storage into distinct zones based on object age, starting with the youngest zone, partition 0. The strategy is simple. Concentrate the collection effort where the yield is highest. By frequently tracing only the youngest generation, the collector reclaims a massive amount of memory with very little work. This memory map highlights the spatial hazard. If the Mutator creates a pointer originating from a stable, mature object in partition 2, aiming directly at a newly allocated object in partition 0, that new object is now live. To find that single pointer, the collector would theoretically have to trace the entirety of the old partition. Doing so would trigger a long execution pause, entirely defeating the purpose of spatial division. To bypass the trace, the system maintains a dynamic side table called a remembered set. This tracks every specific reference crossing from an older partition into a newer one, acting as a direct proxy for the old generation's root set. Spatial partitioning drastically accelerates the collection cycle. But it exacts a strict cost. The system must dedicate significant active memory to maintain and update those remembered sets. The generational hypothesis eventually encounters an inevitable edge case. Some objects survive long enough to be promoted into the oldest, mature partitions of the heap. In this diagram of mature memory, deeply nested, mutually linked structures form complex cycles that span across multiple mature partitions. If the collector analyzes only one of these partitions at a time, the cross-boundary pointers simulate active external roots. The collector cannot verify if the cycle connects to a live application or if the entire tangled structure is dead. Standard generational collectors eventually surrender to this buildup. To clean out mature cyclic garbage, they fall back to a massive, stop-the-world trace of the entire heap. For systems that absolutely cannot pause, architects implement a specialized spatial structure known as the train algorithm. This algorithm reorganizes mature memory into a strict topology. Fixed-size memory blocks, called cars, are grouped sequentially into larger rows, called trains. It is not a traditional trace. It is a highly structured sorting mechanism designed to continuously migrate data until cyclic garbage isolates itself. The system enforces a strict operational constraint to limit pause times. The algorithm only ever evaluates the very first car of the very first train. When analyzing that single car, the algorithm applies two routing rules. First, if an object has a reference coming from an older, higher-numbered train, that object is evacuated outward into that higher train. Second, if an object only has references originating from within its own train, it is kicked to the very back, placed into a new car at the end of that same train. This constant sorting produces a reliable emergent behavior. Valid active data is pulled outward into new trains. Meanwhile, localized self-referential cycles are trapped. They circulate continuously within the first train, unable to escape. The ultimate payoff occurs when a train's remembered set hits 0 external pointers. At that moment, the system knows the entire train is a closed cycle, and it is deleted atomically. The train algorithm guarantees short pause times because it isolates persistent cyclic garbage into disposable, contiguous chunks that can be dropped without a trace. Short pause garbage collection is never a free optimization. It is a continuous, negotiated trade-off between the memory manager and the application's execution limits. This matrix maps the cost of latency reduction. To eliminate temporal pauses with an incremental collector, the system surrenders compute cycles for write barriers. On the spatial side, generational and train collectors surrender physical heap capacity for remembered sets and floating garbage. Modern high-performance systems, whether they are routing global financial trades or serving millions of concurrent web requests, operate strictly within this matrix. Programmers are granted the illusion of a boundless, instantly managed heap, but that illusion survives entirely through the continuous, hidden execution of these precise spatial and temporal compromises.